We're going to get into some cool stuff with exponential growth and decay. So let's understand the difference between exponential growth and linear growth. So let's say you've got $2. Exponential means we're going to multiply, and linear means just to add. So that's why I started with money. Let's say your money doubles every week. That would be multiplying, and that's an example of exponential. So with week 1, you earned $2. Week 2, it doubles to $4. Week 3, it doubles to $8, and then the doubling keeps going, and as you can see, you get very high very quickly. Now, if you were just do linear, linear means to add. So if you started off with $2, then I'm going to add $2 onto that. Add $2, add $2, add $2, add $2, add $2. Wow, look at that difference in week 7 when we have exponential growth versus linear growth. So in terms of money, we always want to use exponential growth. We don't want to use linear growth. But there are times where you'd rather have linear growth than exponential. And we'll look at those as Unit 6 unfolds. This is the basic form of an exponential function. All right, an exponential function has this form. Here's our friend f of x. Remember, you can use any letter, but they generally use f for function. And you can see there's multiplying going on right here. So the general form says we always have a starting point, and that's what the letter A stands for. We have a base, and in the case of this example that we just did, our base was 2 because we were doubling. Again, we're going to get into that a little more in this unit right now. And then x is the time frame. So in our last example, it was weeks, but it doesn't have to be weeks. It can be days, years, minutes, seconds. It can be a lot of things. So now I told you we had exponential growth, and then we had exponential decay. Get that C in there. Well, we saw an example of growth in this first one. Our money was growing quite quickly. Decay means to go down, and you will have decay if the number you put in for the base is between 0 and 1. And we're going to see an example of that in just a few seconds. So here we have examples of what exponential growth and decay look like. Well, it's kind of obvious which one is growth and which one is decay, because growth means to get bigger. As a matter of fact, this one right here is the example we started off with the money. 2 to the first week was 2, 2 to the second week is 4, 2 to the third week is 8, and going on and going on. Over here, this is what we're going to be studying. This is still growth, but this is an example of where you started with $4, $4 chickens, and then everything was tripling. So this was your base. Notice down here we have decay. This is you're losing half of something every single time. I'm taking half away from it. So you're left with a half. And then, can't see it, but right here is a time frame. So how long are you going to keep taking half of something and leaving me with half? This one is a much steeper decay because look at its base. 1/5. You're leaving me with 1/5 of what I started with. So you're taking away 4/5 every single time and leaving me with 1/5. And I don't know why, but we're going to have to change that right now. Don't know why I have to the second power there. That's totally wrong. That should be, obviously, to an unknown. Now, a couple of things about exponential graphs. If you remember, they all have what's called an asymptote. Remember? That's the game that you like to play to annoy your little brother or sister, where you put your finger really close to their head and go, I'm not touching you, I'm not touching you, I'm not touching you. That's what's happening here. Though these graphs look like they're touching the x-axis, they're not. They're getting so close to the x-axis, but they're not really touching it. So if I were to zoom in, you would see that there's definitely some space between their graph and the asymptote of the x-axis. All right, so let's look at an example. This is actually an experiment I ran back in my old school in New Hampshire, and it worked quite well. We started a rumor, and we saw how fast it could spread. And the school, Groveton, was no bigger than Pearson, really. Actually, a little smaller. And boy, that rumor got around real quick. It was kind of fun. So anyway, the number of people who have heard a rumor often grows exponentially. So as soon as you see that word exponentially, hopefully your head is going to go right to this formula, which you need to know. Consider a rumor that starts with 3 people. We remember that our exponential has a starting point. And the number of people who have heard it doubles each day. Hey, and I need a base. I need to know how fast I'm reproducing, growing. So how can we figure out how many people know about the rumor in 20 days? I don't want to do a long chart, but anyway, let's look at this chart to see if we're going in the right direction. So, notice it says 0 gets me back an answer of 3. Remember, in math and physics, 0 tends to mean the initial. Where did I start? I started with 3 people. 1 day later, it doubled to 6. 2 days later, it doubled to 12. 3 days later, it doubled to 24, 48. On the 5th day, it's 96. And I could keep going, but that takes too long. So I am going to figure it out by creating a formula. So my rumor formula, I need a starting point. Well, I started with 3 people knowing it. My base was the fact that it doubles and it's raised to, well, I could do this. I could say it's raised to the d power, and then that means I'm going to have to change some of my letters down here, and n of d. So that means the number of people who heard the rumor depends on how many days have gone by. All right, so let's figure out how many people know it after 20 days. 3, and it doubles to the 20th power. All right, so take out your calculators. So here's my calculator. 3 times 2 to the 20th power. Wow, look at that number. 3,145,728. That is a lot of people after 20 days. 145,728. Wow. That's why rumors spread quickly. All right, example 2. In the year 2000, 50 grams of radium were stored. The half-life of radium is 1,620 years. How many grams of radium remain after 4,860 years? Okay, half-life, and a lot of you don't know this yet because you haven't taken chemistry, is the amount it takes for half of a substance to decay. So if I could do this the long way, I have 50 grams of radium. 1,620 years is what it's going to take for half of that to dissipate, to go away. So, in the year 2000, if I go 1,620 years later, and I were to open up that canister again, there'd be 25 grams, half-life. Half of it would disappear, half of it would stay. If I go another 1,620 years, and I add that onto that, in the year 5,240, I'd still have half of that radium and half would disappear. And if I were to go another 1,620 years after that, you get the picture of what goes on. Let's see, that's 60, that's 8, I think that's 6,860. I'd have 6.25. And I could keep going and going. And you see, the thing with half-life is it never really disappears. Whatever it was, we still have half of. It will never disappear completely. It'll get very minute, very small, but it's never going to go away. All right, so how many grams of radium remain after 4,860 years? So I'm going to come over here and I'm going to try and write a formula to do this. All right, how much did I start with? I started with 50 grams, and my base is going to be a fraction. Remember, it's decay if it's between 0 and 1. So my fraction has got to be between 0 and 1, and it's half-life. So it's saying I'm half decaying, and then I'm having some kind of time. Now here comes the tricky part. We wouldn't put 4,860 up here. We wouldn't put 1,620 up here in this X. We want to understand how many rounds of half-life happened. So in other words, 1,620 goes into 4,860 3 times. So we want 3 half-lives to pass. So when I figure that all out, don't need to go to a calculator because 1/2 to the 3rd power, remember we have to do exponents before we multiply. And when I take 50 and multiply it by 1/8, I get 6.25. That's what we got over here. So in the year 2000, we'd have to wait to the year 6,860, but we'd still have 6.25 grams left.